All right, in this video, I'm going to cover the 5.5 common distribution and 5.6 linear probability distribution. Okay, so the I'm going to cover just the last part of 5.5 first. So the last time we saw the correlation of bivariate normal random variables. So the see. So if X and Y have a bivariate normal distribution with a joint PDF, then the correlation between X and Y must be rho. Okay, so now I'm going to prove that. Okay, so that was, okay, let me see, if X and Y. Okay, this is a 5.5 common joint probability distribution. Okay, 5.5, and then I'm going to cover the correlation of bivariate normal random variables. So X and Y have bivariate normal distribution. Have a bivariate. Okay, normal distribution. Okay. Then so with joint PDF. Okay, so let's say fxy. Okay, the x comma y, and then okay, and the correlation. Then the correlation. I mean the yes, the correlation between x and y is rho. Okay. Now then, I'm gonna prove this. So prove that. So we're gonna first one. I'm gonna introduce two corollary. Okay. So first corollary is expected value of xy is equal to uh, sigma x, sigma y, and then rho plus mu x, mu y. Okay. So it's proof. Okay. So let me start with the definition of expected value of x times y, which is the you know so assuming the x and what x and y, since x and y are continuous random variable, so we have to take a double integral, right? It's x, y, and x, okay, and then x times y, the joint PDF, right? X comma y, and then dx dy. Okay. Now we could express the integrand, okay, is like this: y times, especially y, okay, is the y times marginal PDF of y times the more number marginal PDF. Okay, so this is going to be, by the way, also since y can be considered as a constant in that inner integral, right? Because this is integral with respect to x. So I'm going to bring it out. So integral y, then y, I mean integral with respect to y times, and then I'll put identity y times 1 over y. Okay, so the marginal PDF y times 1 over marginal PDF y, this is 1, right? So that's why I call this one as identity. Then what and then here this one times integral x times fxy, and then x comma y, and then dx, and then dy. Oops. Okay, excuse me. So now next one, and then I'll put 1 over the fy inside the inner integral. So that's going to be here. That is equal to, okay, y integral with respect to y times fy and then y, okay, times inner integral with respect to x times fxy, x comma y over fy over y, okay, and the dx dy. So, but you see, this is actually what x times, I mean f of xy over fy. This is the conditional probability, right? Okay, and then the x times, so that's going to be equal to expected value of conditional probability of x given y value. Okay. Now, and then that is equal to, then, okay, we can say this is equal to the expected value, okay, the y times expected value of x bar y. Okay. By the way, this is the, well, that is mu x bar y, right? Okay. Okay. So, oh, this broken, right? Okay. So, can you see that here, right? So, give me a second. I mean, if you don't get why this is equal to this, because what the that's gonna be what mu x bar y, which is constant, right? And then this is nothing but what expected value of y, right? So we got this. Okay. So now then this is equal to, now that is equal to expected value, okay, of y times. So we saw that what mu x bar y in a second, I mean in the textbook they introduced the what x and y are bivariate normal distribution, then expected value of conditional probability distribution of y given x value is normal with mean, remember that? Mu y bar x, that was what? I mean, is x bar y, right? Right, sorry. Okay, this is going to be equal to mu x plus rho sigma x over sigma y, and then y minus mu y. Okay, okay. So, I mean, textbook, what? Excuse me. Textbook, the give us the expected value, I mean mean of y or y x, okay, x that was given in the textbook. This is mu y and then plus rho and then sigma y over sigma x and then x minus mu x, right? Okay, mu x should be y. Okay, so this is given, but yeah, we'll just switch an x and y, so we got this. Okay, it's not a big deal, right? So I'm gonna plug in this one into here, into right there. Okay, so now then, now y times and then mu x plus, right, rho and then sigma x over sigma y, and then y minus, in this case we have to write down capital letter y, right? It's mu y. Okay, here and here double parenthesis and then close bracket. Okay, so now then what? We gonna give me a second. Y, yeah, I'll distribute y. Okay, so that is equal to expected value. By distributing y, we're gonna get what? mu y times mu x, and then plus rho times sigma x sigma y, and then y squared minus mu y, and then y times y. It's broken. Yeah. Okay. So now then what? That is equal to. Okay. Now we use the linear property. I mean linearity of expected value. So this is equal to y. I mean mu x, because mu x is a mean, right? Mean. The mean of x, right? So it's constant. Okay. So rho is constant, mu sigma x and sigma y. All these three what parameters must be uh constants, and then mu y was a constant. So this is equal to mu x times the expected value of y, then plus rho sigma x sigma y, okay, times and the expected value of y squared, and then minus mu y expected value of y. But what's this? This is the mu y, right? So eventually we got mu square. So this is what? That is equal to what? The variance of y, right? Which is what? Sigma y square. So now, so this is equal to then what? Mu x, and then this is also mu y, right? Mu y plus rho times sigma x sigma y, okay, times sigma y square. Right. So this is equal to this what? Excuse me, mu x and mu y plus rho and then sigma x sigma y. Okay, so I prove it. All right. So we start from what? Exy. We see we start from expected value of x times y. It end up with what? Mu x mu y plus rho sigma x sigma y. Okay. So now then, next corollary. Second. So second corollary is this. Two is the covariance of x comma y that is equal to expected value of xy minus, okay, expected value of x times expected value of y. Okay. So that is equal to then. Okay. Now we're gonna use this by using corollary one. The expected value of x times y is gonna be what? Mu x times mu y plus sigma x sigma y in the rho, right? The minus ex ey is what? Mu x mu y. So mu x times mu y gonna be cancel them out, right? Okay. So now this is equal to then what? Sigma x sigma y and then rho. Okay. So now then what? Yeah, I cover the next part, but let me do it again. Okay. So sigma a second. So now the rho x comma y, that's gonna be what? Covariance of x comma y over square root, right? Sigma x squared, sigma y squared. I mean, which is the what? The covariance is what? From the corollary to second corollary, we figured out the covariance of x comma y is what? Sigma x sigma y times rho, right? Over the bottom one is a sigma x sigma y. So it's just gonna be rho. Okay. Yeah, so now then now next one we move to 5.6. Okay, so linear functions of random variables. So we'll do right here. What's this? Okay, so linear functions of random variables. So yeah, in this section, yeah, you can see in my lecture note, but results for linear functions are highlighted because of their importance in the uh, remainder of the book. Okay, so we're gonna use the property we're gonna study in this section a lot. Okay, in the remainder of the book. Okay, so okay, let me also give you a simple example of linear functions of random variables. So For example, so think about this. The random variables, okay, random variables, x1 and x2. Okay, so this is 5.6, by the way. Okay, 5.6 linear functions of random variable. So x1 and x2 denote the length and width, respectively, of a manufactured part. Okay, so the length and width, okay, length and width, respectively. Okay, let me skip writing respectively, okay, of a manufactured part. And then now we define new random variable y is equal to 2 times x1 plus x. I mean, yeah, okay. So then y is also, yeah, so once we define y as like this, linear combination of x1 and x2, right? So 2 times x1 plus 2 times x2, right? So then that y also a random variable that represents parameter of the part, okay? So now then, start from the first topic, linear function, okay? So given, so we're gonna generalize this example, okay? So for given random variable, okay, x1, x2 through the xp, okay, and a constant c0, c1 through the cp, did we define y, okay, as a linear combination of random variable x1 to xp with a coefficient, okay? So this is c0 plus c1 x1 plus through the what, cp xp. But actually this is equal to what? Sigma, right? Okay, sigma I equals what, 0 1 through the p, okay, and then ci x xi, right? Sorry, c0 plus, I forgot this one, c0 plus sigma ci xi, right? Okay, there is a linear function of x1 through the xp. Okay, this y is called what is a, oops, this is a linear function of x1 through the xp. Okay, then what about expected? Let's figure out expected value, and then I mean mean and variance, okay, and then covariance and correlation, okay. So e of y, that's gonna be what, the multiple integral, right? So the c0, right? c0 plus sigma I equals 1 through the p ci xi, right? Oops, okay, times what, the x1 through the, oh, we don't have a comma right here, just xp, and then join the pdf, right? x1 through the xp, that's the joint pdf, and then dx1 through the dxp. Okay, now then what, this is equal to, okay, that's gonna be, so this is anyway, it's a linear combination, right? So we distribute that joint pdf inside the bracket, and then we separate, okay, since this is linear combination, so we can separate that multiple integration as the what, integral of c0, and then integral of, I mean c0 times join the pdf plus integral of c1 times x1 times that join the pdf with respect to x1 plus, you know, multiple integral of c2 times x2 times that join the pdf with respect to x2, with respect to x1 through xp, sorry, okay. Understand what I'm saying? So this is equal to c0 times the multiple integral, the fx1 through the xp, and the x1 comma xp, then dx1 through the dxp. Okay, See the plus, yeah, and then plus, okay, and what? C1 times, okay, multiple integral, and then x1 times fx1 joint PDF. The x1 comma xp, and then dx1 through dxp. Okay. All right. So now then what? And the plus, yeah, let's keep going, right? So plus through the last one must be cp, right? cp times the integral, and then xp times fx1 xp, and the x1 through the x comma xp, and then dx1 through the dxp. Okay, so then what? Look at this. The multiple integral of joint PDF with respect to x1 to xp. This is 1, right? Okay. Keep in mind this. The integral of joint PDF on the entire domain must be 1, right? So this is 1. So C0 gonna be left, right? So, and then next one, the next time, C1 times integral of multiple integral of x1 times joint PDF. That's gonna be a definition of the expected value of x1. And what? This is gonna be what? CP times expected value of xp. So finally we got this. It's going to be what? C0. Okay, can you see the C0 plus expected value of x1, C1 times, oops, plus C2 times expected value of x2, plus through the CP times expected value of xp. Okay. So now then, that you see that if a new random variable is defined as a linear combination of the given random variables, then expected value of that new random variable going to be what? Just a linear combination of expected values of the random variables given. Okay. So this is equal to what? C0 plus sigma I goes 1 to the p. Okay, and then ci times expected value of xi. Okay. So now we can say that what? Y is equal to sigma oops, sorry, not this one. So y is equal to c0 plus sigma I goes 1 to the p, okay, and then ci, and then xi. Then expected value of y is equal to c0 plus, okay, then sigma I goes 1 to the p, and then ci, expected value of xi. Okay, so keep in mind this. So and this is trivial. This is trivial kind. Yeah, actually, why? Because expected value is just satisfy linearity. Okay? And the y is defined as a linear combination of the xi. So the what are variance, by the way? V of y. That is equal to c1 square and then v. Let me accept this one without proof. Okay. C1 x1 plus c2 square and then v of x2 plus through the cp square, okay, and then v of xp plus, minus, there's plus, and then 2 times sigma, and then sigma, and then I is less than j. What does that mean? So this is, let's say this is sigma of I, this is sigma for j, okay? So I and j are moving indices, but we're gonna choose I and j such that I is less than j, okay? So the ci and the cj and the covariance of xi comma xj, okay? Keep in mind this. Right. So now next one, the third one, if x1 through the xp, okay, that are independent, x1 through the xp are independent, Then what happened? Then what happened to the variance? It's gonna be what? That covariance term will be gone. Okay, because it is trivial. Why? Because x1 through xp are independent. That means what? Covariance of xi, xj must be 0 for any choice of I and j, right? So except for what? For any choice of I and j, except for I is equal to j. But you see that I is less, and we're gonna add this one for only if I is less than j. So okay, so now this is gonna be c1 square v of x1, okay, plus through the cp square and the v of xp, which means that this is equal to what? Sigma, okay, I goes 1 through the p and then ci square and the v of xi. Okay. All right, so that covariance term is going to be gone if x and x1 through xp are independent. Okay. So now next one, see example. Okay, I know it's quite too many formulas I introduced, right? So let's see example. So let's say x1 and x2, x1 and x2 are not independent. Okay. All right. So then now let's say y is defined as x1 plus x2. Okay. All right. So you see that y is defined as a linear combination of x1 and x2, right? Okay. And the x1 and x2 are not independent. What does that mean then? When you find out the variance, you have to apply this one, right? Not this one. No. Okay. So first one, let's find the covariance. Okay. Covariance of x1, x2. That's going to be expected value of x1, x2, right? Minus mu x1, mu x2, right? So now then that is equal to what? So here, can you see that? Y is equal to x1 plus x2. Okay. Yeah, I missed the one more information. Sorry. Let's say x1 and x2 be random variables, and x2 is equal to negative x1. Okay. Then not let. Okay, so then sorry. Then x1 and x2 are not independent. That makes sense, right? Because x1 there is x2 is, I mean, there is a relationship between x and 2, x1 and x2, which is x2 is equal to negative x1. Definitely x1 and x2 are not independent because the value of x2 is determined by what? The value of x1. So now then, from here, so I'm gonna plug in what x negative x1 into x2. Okay, let's see that here. Let's see right here. I'll plug in negative x1 into x2. So then we're gonna get this expected value of negative x1 square, right? And then minus mu x is e of x1. So I'll try. I'm gonna express every single x2 in terms of x1. Okay. So times, and then mu x2 gonna be what? Expected value of negative x1. Okay. So see that? Yeah. Now then, this is equal to, okay, be what? Expected value of negative x1 squared is what? Negative expected value of x1 squared. Okay. And then plus, okay, this is also what? That's going to be what? Is equal to negative expected value of x1. So we got this. Negative expect e of x1 times negative e x1. That's going to be e of x1 square. Okay. Okay. Give me a second. Why is it so blurry? Second. All right, so now, okay. So now that is equal to, okay, so this is equal to negative, right? Expected value of x1 square minus, this is what? Mu x1 square, right? So actually this is a negative variance of x1. Okay, let's see. Now let's find out Vy. This is equal to Vx1, right? Plus V of x2, and the plus 2 times covariance of x1 comma x2, is it? Okay. So now this is equal to, but what? Vx2 is what? That is equal to negative, V of negative x1, right? Okay. All right. But actually, remember that, what? Here, variance of ax plus b, that was a squared times variance of x, right? Remember that? We learned this one now. I think chapter 3. So then variance of, variance x2, that is equal to variance of negative x1. Right? Variance of x2 is equal to variance of negative x1. That is equal to negative 1 squared times variance x1, which is variance of x1. Okay. So we got 2 variance of x1, 2 times variance of x1, right? Okay. And the plus 2 times covariance of x1 comma x2. Covariance of x1 and x2, we just got this one. But we just figured out this one, right? Which is what? Negative variance of x1. So we're going to get negative 2 times variance of x1, which is 0. Okay. All right. So the last one, let's figure out the correlation of x1 and x2. Okay. So correlation of x1 and x2 is going to be what? Covariance of x1, x2 over standard deviation of x1 times standard deviation of x2. Okay, keep in mind that. Then what? We just got covariance, right? What is this? Negative vx1, right? So negative v of x1. Oops. Negative v of x1 over sigma x1 is what? What? The what? Give me a second. So give me a second. Here vx2. Sigma x2, which is what? Sigma x2. Sigma x2. That is gonna be variance of x2. This is equal to variance of negative x1, which is what? Negative 1 squared times variance of x1, right? Which is sigma x1, right? Okay. See? So we got this. Sigma x1 times sigma x2 is nothing but sigma x1 times sigma x1, which is sigma x1 squared. But sigma x1 squared is what? Variance of x1. Right? So we got negative 1. You see the correlation, we got just negative 1. It means that what? Let's say this is the representative probability. Random variable x1, this is random variable x2. Then the distribution of the data must be like this. Okay. Now see example 5.25. Okay. So example 5.25, they're talking about the negative binomial distribution. Negative binomial distribution is random variable in the negative binomial distribution is a linear combination of geometry random variables. That's why expected value and then variance, negative binomial distribution, follow the rule what we just studied here. Okay, so which one? Yeah, expected value of the y is like this. Okay, and the variance is also like that. Okay, I show you. Okay, so example textbook. Okay, 5.25. So let me review what is the negative binary distribution. So review. So negative binomial distribution. Okay. So first one, the random variable. Okay, x that is equal to number of Bernoulli trier. Okay, until R successes occur. Okay. Yeah, let me go over binomial distribution and the geometric distribution and the negative binomial distribution. So binomial distribution, the random variable of x is the number of successes. Okay, and then geometric distribution, the random variable going to be number of the Bernoulli triers until we get first success. Okay. The negative binomial distribution is a general version of geometric distribution. The random variable of x denote the number of Bernoulli trier until R successes occur. Okay, so binomial distribution, the total number of Bernoulli triers is fixed. Okay, but geometric distribution and the binomial distribution, number of Bernoulli triers is random variable. Okay. And then geometric distribution, we assume that it will happen just one success, but binary distribution, number of successes can be manipulated. Okay. So now next one is a p that is equal to, here p is just constant probability of success for each trier. Okay. So the constant probability of success. Okay. Sorry, so blurry. Yeah. Next, third one. The PDF. Okay, so the probability density function fx is going to be x minus. Combination of x minus 1 over r minus 1 times 1 minus p to the x minus r times p to the r's power. Okay, so definitely x must be greater than r. Okay, r and then r plus 1 through the. Okay, and then definitely x cannot be exceeded the total number of Bernoulli trier. Okay, so now then the negative binomial random variable. Okay, this one is so what negative binomial random variable is represented as a sum of geometry random variables. Okay, let me say geometry. Okay, geometry random variables. So what that means, think about the trials, Bernoulli trials. First trials, okay, this is second trial, and third trial. Let's say third trial we got first success. Okay, all right. So now then, what that's gonna be? Let's say this is x1. Okay, x1. Then what? here, that's gonna be 1 through 3. That's gonna be what? The geometry random variables. So geometry random variable here, x1, okay, x1, see? So x1 can be 1, 2, 3, okay? So x1, 1, 2, 3, that's gonna be positive values of geometry random variables, x1, okay? And then now, starting from here, and then fourth trier, and the fifth trier, and the sixth trier. So let's say we got the second success at 6 triers. Okay. By the way, this is the first success. Okay. This is the second success. Then let's say this is x2. I mean x. Let's say define x2. Okay. Its possibility is just what 3. I mean 4, 5, 6. Okay. Let's see. Right. And then x3 gonna be 7 and 8. So we got the third success right here. And then this gonna be what? X3. Okay. So x1, x2, x3, these can be considered as what geometry random variables. Right. So now then, okay. So let's say y. Okay, let me say y be a negative binary random variable. Okay. Then y can be expressed as x1 plus x2 plus through the xr. Okay, where xi is a geometry random variable. Okay, with the parameter p. Okay, and they are independent. Okay, and then e of y. Okay, implies e of y going to be what? Sigma, right? The expected value of xi, the I goes 1 through the r. Okay, by the way, and so on, and so on. Okay, then there's going to be what? There's going to be, but e of xi, since what? x1 through xr is what? Geometry random variable. The expected of the geometry random variable is what? 1 over p. So this is equal to sigma I goes 1 through the r, and then 1 over p, which is r over p. Okay. All right. The next one, what about the variance? Variance of xi is going to be 1 minus p over p squared. Okay. Okay. So that's the variance of geometry random variable xi. Then applies the variance of y. That's going to be what? Sigma. Okay, we don't have to figure out the what covariance. Okay, we don't apply this one. We apply this. Why? Because what? X1 through XR are what? Independent. Okay, so we don't have to figure out the covariance. So this is equal to I goes 1 through the P, and then V of XI. So that is equal to R times 1 minus P over P squared. Okay, let's see. Okay, so let me stop here. Okay, I'll continue to yeah, I'm going to continue from the example 5.26 okay, the next time. Okay.